afternoon to everyone, both online and offline. And I'm very happy to welcome you in today's celebration of this National Technology Day. And it is actually a great pleasure and that we are organizing this event jointly with Indian National Academy of Engineers. So in that way, it's very appropriate. A basic science institute joining hand with the engineering academy. So that is how it should be. And so it's a very fortunate coincidence, I would say, because I approached Professor Manna for giving a talk, and then he said, why not we organize it jointly? And I said, I'll be very happy to have it organized jointly. And we have 3 speakers in our session. One will be small talk, one will give medium talk, another will give long talk. And I encourage all of you to interact very actively because that is the purpose at the end of each talk. And I now request our governing body chairman, Professor Jagatav, who is from IIT Bombay and previously he was from BRC, to formally start this event. And he has another hat. He is also chairman of the National Advisory Committee of the Technology Research Center we have in this center. So, I think mic is not working. But with both there will be a mic.
No, it's not working. Okay.
Professor Leonardo Manna, who is joining us online. Professor Suman Chakravarti, who is yet to arrive. Professor Samit Kumar Ray is right here. Professor Tanusi Das Gupta, faculty members and students of SN Bose Center, distinguished invitees, ladies and gentlemen. On behalf of this center and on my own behalf, I extend a warm welcome to you all to this very special function organized to celebrate the National Technology Day 2022. We are indeed elated to celebrate this day in association with the Indian Academy of Engineers and in the august presence of Professor Munna, Professor Chakravarti, and Professor Ray. I profusely thank them for accepting our invitation and agreeing to deliver talks here. To my mind, this is a recognition of SN Bose Center as an institute for technology development. And thanks to the successful completion of the phase 1 of the Technical Research Center program, I'm pretty hopeful that the center will continue to enhance its standing in technical research and technology development in the phase 2 of this program. Friends, as we are aware that 11th May is celebrated to commemorate the successful demonstration of indigenous nuclear technology for the purpose of national security done in 1998. We are all indeed proud of the achievements of our technologies. At the same time, today is also a day when we need to remind ourselves of the task lying ahead of us. Friends, since 1998, the priorities of technology development have changed significantly. To mention just one issue, with the UN Agenda of 2030, the issue of technologies for the sustainable development has taken a center stage. We also know that presently the university rankings are based now on the Sustainable Development Goals. MIT has already started a big program on climate change. There is large amount of activity going around in the world, but it appears that we are still to make headway in this direction. I'll just cite one example. As we know that there is much talk about the hydrogen energy in the country, and the policy for the hydrogen energy has been already unveiled. If we talk about what is the technology level of hydrogen production, I just give you some figures. We know that energetically 1 kg of hydrogen is equivalent to 39.4 kilowatt hour. Now the capillary fed electrolysis technology can produce hydrogen at 41.5 kilowatt hour per kg. Whereas I was reading just 2 weeks ago, the water vapor electrolyzer technology has crossed that threshold by achieving it at 35 kilowatt hour per kg. It's a very, very significant development. And compared to that, we need to go miles as of now. There are several other examples where many technologies have taken rapid strides in the recent years. We are thus at a crossroad yet once more. Until yesterday, after independence till yesterday, we imported environmentally aggressive technologies from the West in the hope of the economic prosperity. And irony is that tomorrow we are likely to import environmentally benign technology from the same places. So we become the importers all around. And our next generation is likely to blame us for missing yet another bus, which we have been missing so many times. So on this day, we need to ask ourselves, where do we fall short? If you may allow me to draw from the theory of knowledge management, I may say that we as a country are in a technological chaotic state. There exist ideas, there is expertise, there are skills, but they are in such a chaotic form that they do not add to make a difference. This is a state like a diabetic patient. There is enough sugar in the body cannot take that. We need self-organization and a strong will to graduate to the next level. That is the technology-enabled state, and finally to the technology-centric state where we will have answers to every problem this country has, and where we do not need to import ideas and technologies from outside. This is where the Atmanirbhar Bharat dream will begin with. This is a Herculean task that we have on our hand today. I sincerely hope that the science and technology community will reorganize itself to meet these current challenges. Therefore, friends, on this National Technology Day, we all rededicate ourselves to this important task. Surely, we should be able to make a difference in the near future. I welcome you once again to this function and wish you happy National Technology Day. Thank you, one and all.
So the next line is Professor Shomit Ray, who is currently professor in the physics department at IIT Kharagpur. In fact, there is a strange coincidence also, because all three speakers of today, they have IIT Kharagpur connection. Either they were in IIT Kharagpur, currently in IIT Kharagpur, and so that tells a lot about that place. So he was also former director of our center and the key person in implementation of TRC phase 1 at Esango Center, which has been mentioned by Professor Jagda. He is fellow of INAE, so that makes definitely justifies him to be a speaker, which is jointly organized with INAE, and Indian Academy of Sciences, Lahore, and West Bengal Academy of Sciences. His research interests lie in the broad area of experimental condensed matter physics that focus on semiconductor nanostructures, differential growth of quantum structures, nanophotonics, and the physics of nanodevices. His studies on gallium and germanium quantum dots trained germanium to achieve light emission from an indirect factor. Semiconductor is considered to be very useful and show the way to realize the silicon-based laser in future. And he is going to brief us about the translational activities, especially within the ambit of the TRC that were taken up at SNBNCBS.
Yeah, thank you, Professor Shadash Gupta, for inviting me to say a few words about the TRC, which is basically Technical Research Center established at the SN Bose National Center for Basic Sciences on this auspicious day, National Technology Day. Of course, I will not make any formal presentation because since all the TRC pages are there, but probably I'll say a little bit on the history and how much we achieved. Just not the quantitative number, just to give an idea that whether really a basic science institute could contribute to something to the technology. So before going to the actual TRCs, okay, let me say that TRC is basically that's called Technology Research Center. So DST 2015 decided to set up 5 technology research centers in 5 DST institutes: Suchitra Institute, Trivandrum, ERCI, Hyderabad. These are more or less the 2 institutes working on kind of a translational research, applied research, working with industries. Suchitra had their own hospitals, a profit-making company, Section 8 company, everything was there. But other 3 institutes were chosen are basically Basic Science Institute, JNCSR Bangalore, Association for the Cultivation of Science in Calcutta, and of course SN Bose National Center for Basic Sciences. I don't know how these 3 institutes are chosen for this, because afterwards there were many other DST institutes are complaining that we are not giving in scope to write a project. But somehow it's some consequence that afterwards in the last few years we need to see the academic progress of these 3 institutes. These 3 institutes are the top 3 DST institutes in terms of the nature index ranking. But I'm sure at that time that was not the criteria, because the criteria of the TRC was ultimately you have to develop some technology, you have to deliver some product, you have to make some prototype. So, of course, there was doubt, there was questions, because I also joined at the time when the TRC project has already been approved about a year or so. And unfortunately, at that time, there was no regular director, there was an officiating director who was not in the institute, who was outside. So obviously there were some doubts, there were some questions whether these basic science institutes will be able to deliver the products or the deliverables from this particular project. So of course I gave a thought. I was also asked the same question in the interview, that what is the vision, how do you think? So then the question that the answer firstly that I got is to my mind. The division between this science and technology is not created by God, not created by nature. It has been created by the humans themselves. We have created the boundaries that I do science, he does technology. This is not correct actually. Both science and technology have got the same goal. Both needs hard work, innovation, intelligence. And ultimately the output at the end of the both of them is, of course, that benefits to the society, training of manpower, and a huge development. Only thing that technology, always what you do in the technology, it's immediate application there in the societal applications or practical application, and whatever science does today probably it will be actually applied or find its application maybe after 20 years, 30 years, after decades. So this was just a kind of a man-made, and that perception was always there in my mind. So before I go to TRC, I just tell two of my experiences because I thought this is just a formal lecture on the technology day. So when I was a student, I just graduated from my undergraduate BSc from, of course, this was under Calcutta University one college. They was trying to be getting admitted to master's course, MSc. So I had the option to go to either traditional university like Calcutta University, or I got an admission at IIT Kharagpur. So with not much having some idea that which institute is better, there was no NIRF, there was no age index, no citation, etc. I had to take advice from some of the seniors and some of the even the faculty members or the professors. But strangely, even some of the faculty members and professors advised me, no, you should not do an MSc from an IIT. They are technical institute, they are engineering institute. Your MSc degree will not be recognized. So sometimes if you give an interview for a faculty position somewhere, maybe you'll have a difficulty in getting a job. But anyway, so I had to take some decision which I took at that time. And almost the similar kind of question I faced when I joined here in 1986 and addressing the faculty, meeting the faculty for the first time. Since there was some doubt, even with the faculty members, that how much will deliver, some senior most faculty member asked me a question, very aggressive question. Do you think that we should have a technical research center at all in SN Bose National Center for Basic Sciences? So it's basically, is it not a conflict? Because on the one way you are calling basic sciences and one way you are calling technical research center. Is it not kind of a conflict with our mandate, conflict with our bylaws? So obviously that I had to convince him. This is the project we have taken from the government of India, and by that time government of India has already established some policy for making India program. So, and we are under Department of Science and Technology. So there is no way that we'll say that no, we will not do technology, we will do basic sciences. So obviously, but fortunately that there are some problem, of course. The biggest bottleneck was that there is no ecosystem. That's not possible because it's a very, very small institute, small number of faculty members. People are working in diverse areas. Maximum probably 50% of the people are working in experiment. And by even if you take the computational sciences as a kind of a applied sciences, and maybe other 50% was more or less on theory. Even you will see that patents, etc., was very, very rare at that time. Probably the institute had 2-3 patents in its history. So it is more on manpower training, doing PhD, doing research, etc., for the students. So there was a huge challenge, but fortunately, that whatever the resources that we had, particularly faculty members who were the PIs of the so-called TRC program, they give their, they give them, I don't know what is 100% or 200% or 500%. So they give their best. So actually they were doing already some science or the innovation on the topics. They have already written the projects. The project was basically based on expertise on materials, spectroscopy, computational tools. So it's already there. So now actually you have to bring them from the science to technology. And project is already over by a year. So another 4 years you have to count some deliverables. And it was very clearly told that publication of paper is very welcome, but that will not be considered as deliverables. You have to really, so within 4 years, the faculty members with their untiring efforts, and of course there was extreme support from the administration also, because everything was new. Even we don't know how to sign an MOU with the institute. We don't know how to sell technology because there is no legal sale, there is no IPR sale, nothing is here. So everything is new. So there was a very, very, administrative support, and then we established some MOU with NRDC, National Research Development Council, who can help us with kind of a technology transfer if we really develop some technology. Of course, patenting, etc., we have our patent lawyer, we took their help, and by the kind of end of the first phase, or within the 4 year, the faculty members came with their 24 patents. Of course, some of them are filed, some of them are approved. One of them are, of course, international, and 7 technology transfer was done by this 4 year. So technology transfer means that you have found an industry who is happy with your prototypes, And all these prototypes, most of the prototypes were based on the healthcare, say non-invasive medical diagnostics, on which Professor Chakraborty will be giving his talk today. And almost all these technologies were developed in collaboration with the doctors in different hospitals. So that's why it was very, very easy to sell the technology to some of these companies. And I feel that was not only I, in fact, the project was so-called monitored by National Advisory Committee. So the chairman of the governing body, that time it was Dr. Shiku Armayati, he was the chairman of the NAC. And at the end, it is right now, Professor B.A. Jagtap, he is here today. So even at the end of the first phase of that project, the NACs were extremely happy. They said that it has gone beyond our expectation, that a basic science institute will contribute to so much of technology transfer. Then not only technology transfer, revenue generation, almost 1 crore of revenue was generated. About 80 lakhs were generated through the technology transfer, patents, manpower training. So this was definitely the investment made by government of India for making this TRC was definitely successful. So 5 years back, there was no ecosystem. So right now there is an ecosystem. But there are some challenges, of course, that now probably the TRC2 will be coming, because that proposal was sent to DST long back when I was here even. So, and of course there is extension, but the question is that how long and how will be the sustenance? So that is one question probably only the SNBNCBS Center cannot answer, to be very frank. This has to come from the policymaker, administrators, that there has to have some sustenance policy. That, because one of the other problem, Chakraborty, Suman Chakraborty is the Dean Srik also, right now, Dean R&D right now, it was not Dean Srik. And he knows that he has got some other people who helps him in the administrations for there is step in IIT Kharagpur. Somebody can incubate, somebody can start up in the technology part, but all these DST institutes cannot have an incubation center. So we have to initially in our aim it was kind of a setting up an incubation center. So in the middle you have to this incubation center means you have to open a Section 8 company. And for that, you have to go up to the cabinet approval for doing this. So ultimately, the name was just to Translational Research Center. So that you make prototypes, make something, then let the industries come. So the question is that, so that's the future challenge you have to see, that how much the faculty members can contribute to this. And particularly if you really sustain this one for the future growth of India. And by the time that we have more and more emphasis on the Make in India, the self-reliance in technology, that problem with China, it's importing from China, all these problems are there. So this has to be really solved. I am sure the chairman, Professor Jagtap is there, Professor Shadash Gupta, the DST has to help. So definitely there should be more collaboration probably with already that existing incubation center at different places. We already had this thing MOU with IIM Incubation Center, probably IIT Kharagpur, there can be a MOU with IIT Kharagpur. Maybe startup companies can be incubated there and our faculty members can be just consulted. In fact, in SNBNCBS Center, even the faculty members cannot take the consultancy fees also. There is no legal rule, etc. like this. So many things have to be done. So these will come after the TRC, the second page, that how it will sustain. But definitely that the investment that has been made actually created a lot of manpower. Excellent laboratory facilities have been created, a lot of experimental facilities, those things have been created. These are probably very, very rare. Even if you see, even ICPC, IIT Kharagpur, the kind of huge IIT Kharagpur and see the SNBNCBS National Center for Basic Sciences, the experimental facility available for faculty members or for students, you just cannot compare. So that is one thing that probably you could do because of this kind of a mega projects also. So this was an opportunity, and I will say what is the faculty members and the PI who participated in the project, they have really grabbed the opportunity very well, and they have demonstrated their potential. But obviously, that final kind of a applications and final kind of a sustenance, that point probably has to be taken care of. Just only two more things. So since Professor Chakraborty is also here, maybe in future he will be also interested. the 7 technologies that were actually transferred to the different companies, almost all of them are all non-invasive healthcare diagnostics. So basically non-invasive detection of bilirubin, hemoglobin, oxygen deficiency, which was a huge problem during the COVID time. Then detection of the jaundice in neonatals, while you cannot really pick the blood from that the baby. So I think these are some of the, then of course Professor Manik Pradhan is also here, then the non-invasive detection of ulcers, basically hyper, bacteria, helicobacter, I'm sorry, so some very, very special bacteria which creates ulcer. And then a lot of prototypes are ready, particularly in the sensors based on the adulteration in the food, air, water. So I'm sure that, and one very good thing is that 2 things that actually it has helped. Firstly, there was a very, very good collaboration, not only among the scientists, but between the experimental scientists and so-called the theory or computational physicists, particularly Professor Shadar was involved in 2-3 projects. So that was very, very rare. So that has created, so that has catalyzed, the TRC has catalyzed that kind of collaboration. And one more very good thing, the new faculty members who have joined, so 3-4 faculty members, they would actively participate. So this is one very good thing from the very beginning. You know that in addition to your basic research, you have to do something on the translational research. Because that question will be asked definitely always by the government, that we are giving so much of money. So what is your contribution to the society? So the development of prototypes, patents, technology, it has to continue. Whether we have got TRC or not doesn't matter. This has to be asked. So I'm really thankful to all of you, and very privileged to be here. With lots of memories for the last. In fact, last year in the month of May also I was there. So lots of sweet memories, happy memories, and be able to see that our students and thank you so much for the invitation.
He says his video is on. So welcome Professor Manna. So our next speaker in today's event is Professor Hydrogel Manna, and he is currently the president of INAE. So since we are having it jointly, we are very, very grateful and thankful to him for giving your time in this joint event. He is currently the fifth semester G, and he does CGCRI. He is a fellow of all 3 National Academy of Science, as well as of Engineering. He is the recipient of World Sciences Prize for Engineering Sciences and also a elected fellow of Bose. I think there is a background.
सब बोलते हैं जैसे पानी में पुदीना डाल के रखो पीते रहो
So he is a recipient of the World Academy of Sciences Prize for Engineering Sciences and also elected fellow of Bose, in addition to the Indian Science Academies and Indian Engineering Academy. He is a materials engineer with a wide range research interest covering phase transformation, structure property, correlation, modeling in nanometric materials, ceramics. So it's a very diverse research interest. And today he is going to tell us about science, engineering, technology, synergy, and role of INAE. Professor Manna.
Thank you very much, Tanushree. I think I should be able to upload a file.
Your voice is very feeble.
Why? I'm right in front of the laptop.
Yeah, your voice is very feeble. Can you hear me? Your voice is very feeble.
I see. but I'm very close to. Let me see some.
No, it's okay.
Is it okay?
I can hear it properly.
Yeah, yeah.
Okay. So let me try to yeah, file upload. I'll just first try and upload the file. So how do I?
Just click on that one, then share.
Is my screen visible?
Not yet.
Not yet.
It says present. Can you just can you keep that?
Yes,
No, his screen is visible. Yeah. Stop.
Is it okay now?
Yes, it is.
Can you see my first slide?
Yes.
Okay. Okay, so let me start. And at the outset, I first would like to record our deepest appreciation to the Bose Center, SN Bose Center for Basic Sciences in Calcutta, and in particular, its director, present director, Dr. Tanushree Sahadas Gupta, for actually, it was me who made this proposal to Tanushree that can we not do it together? And this certainly sets up the stage to propound the theory of synergy between science and engineering and technology. I am also honored to see that Dr. Jagtap, who is the chairman of the council of SN Bose Center, is present, and so is Professor Mitre, the former director and a good friend of mine. And I assume that a large number of faculty colleagues from Bose Center are present. Also, my colleagues, fellows of INAE, the young associates, young engineers, and awardees of INAE, members of the Kolkata chapter of INAE, and all those who actually are interested in understanding and tracing the path of progress for this country through the synergy of science, engineering, and technology. So very good evening to all of you. I'm speaking from the head office in New Delhi, head office of Indian National Academy of Engineering in New Delhi. My apology for not being able to present in person at the venue. But in today's world, it really hardly matters anymore as to who is speaking from where, because thanks to this huge connectivity offered by the digital platform. So as I said, the thesis that I would like to propose and propound today is the essential synergy needed for sustainable growth. And that synergy actually should have complementarity among the three very important components of societal growth, namely the science, engineering, and technology. Dr. Jagtap mentioned, and let me also repeat, that this is a very momentous day for the nation to remind ourselves not only about the past achievement in terms of the Pokhran 2 explosion in 1998, but also the bigger strides made in terms of our defense capability, our major achievements in science and technology. And it's not just confined to the military hardware or energy security or overall defense security of the country, but also percolates to food, health, in terms of, let's say, the green revolution, the white revolution, and now we talk of blue revolution. India also has received a very large amount of accolades from throughout the globe in waging a very important battle against the COVID-19 pandemic. In fact, India is now acknowledged as a leader of this battle. Which,
Dr. B.C. Roy, PhD Engineering, M.Tech, PhD Engineering.
somebody has to again help
1970
me.
কোথা থেকে আসলো?
Yeah, okay. So, so essentially, the country is making all-out efforts since its independence, and in our 70 plus years of record, we have had very many achievements, but the fact remains that it is not always enough. At the same time, one must use this opportunity and platform to rededicate ourselves to the overall growth of the nation. Now, the obvious question is that why do we celebrate National Technology Day? As I said, it is primarily to remind ourselves of the past achievements and at the same time use this occasion as an opportunity to pledge that the country needs to cover a long path ahead. And that long path actually requires, in my opinion, not just technology alone, because technology doesn't come ab initio. Technology is built on the foundation laid by science and further taken ahead through engineering and technology. So the next question is that why do we need technology? The simple answer to that is that each individual, whether it's an individual or a collection of individuals, we all aspire growth and prosperity. And in today's context, anywhere in the world, the prosperity can never be thought or sustained without the insurance of science, engineering, and technology. So if we want to secure better life, improve healthcare system, augment the infrastructure, ensure better connectivity, faster communication, in all aspects, we need new technology and affordable technology, technology which is environment friendly, and most importantly, technology that is sustainable. So for that reason, it is absolutely essential that a country, while ensures society and security, also devotes enough time and attention for scientific pursuits, engineering interventions, and eventually technological innovations. So for a while, if we consider science, engineering, and technology as if they are independent and separate entities, then I would simply propose that science is simply know why, engineering is know how, and technology is know what or what sells in the market. And you would have seen this kind of cartoons before in some of my lectures on the same theory, but no harm in repeating them because the relevance of this synergy or the need of that remains as important as it was yesterday. So nobody knows whether actually an apple fell on Newton's head, but what is absolutely known is the fact that he was the first person who raised a very serious fundamental question as to why an apple should actually fall onto the ground from the tree and not fly above. So that helped him to pursue the science and eventually find an answer to this fundamental question of know why, as to why should apple fall and not go up, and came up with this universal laws on gravity or gravitational forces. And this is absolutely essential today because today we would like to not only stay only on the surface of the Earth, we would like to go beyond the Earth's atmosphere and then explore the space. Whether it is space exploration or flying an aircraft or building some other aerodynamical theory-based objects, the laws of gravity remains the fundamental or foundation stone for any such pursuit. So Newton never actually imagined that someday we'll use it to fly a rocket to the moon. But engineering comes handy in that. Now, Da Vinci actually, when he drew this particular sketch, he actually tried to give a shape to human aspiration to fly like a bird. And it took 2 more decades or 3 more decades, after which the Wright brothers, they were able to show the first flight of a human-made flying machine, the aircraft. Though the flight lived only 18 minutes, but eventually that paved the way for the air connectivity today that actually is so handy and so important for all of us. And as I said, that India also is now one of the nations which actually is aspiring to go as far as the Mars, explore, and even to the moon, surface of moon. It gives us an impression that this is the sequence, that science, then engineering and technology. Not always so. You all are aware, particularly in Bose Center, that Einstein proposed a gravitational theory or gravitational wave way back in 1916. It took exactly 100 years in 2016 to have founded this famous laser interferometer gravitational wave observatory, or LIGO, to prove the existence of gravitational wave. So while science helps technology to be founded, technology also proves that the scientific prediction was right. So that's why I say that there has to be interconnection or a synergy. So science actually is always championed by the likes of Newton or Einstein and our own Indian icons like C.V. Raman and J.C. Bose. But in order to take the curiosity-driven act leading to occasional discoveries to greater goods, we need engineering, which actually converts these fundamental knowledge into certain products and devices through engineering inventions. And this is where you actually need the Wright brothers or Edison and the likes. And then finally, to actually reap the benefit and take it to the society, you need not only multiple copies, you need certain incremental developments or improvements through innovations so that the item becomes cheaper, more affordable, more energy efficient, more environment friendly, and so on and so forth. Because the device that we use today, even if it is the most expensive and the latest, there's no guarantee it will remain the latest and the top of the bench forever. And that happens because all the time, society sitting at the centroid of this triangle always demands something better, more efficient, cheaper, and so on and so forth. So in order to pursue this path, we have to understand that the society or the ecosystem in the society has certain components which feed into each other. The academia creates knowledge or disseminates. That's what we do as teaching or research. The research organizations like Bose Center or many others in the country at times come up with major inventions, and these inventions make their way to the commercial production through industry. And that's when a viable technology emerges through certain innovative solutions. And this cycle continues because society continues to demand, as I said, not only consumes, but continues to demand something always should be of a better and higher quality. So in order to pursue this path of science to engineering to technology or synergy between them, we often try to pursue the path of innovation through research and development. And as you can see, and all of us are aware, that as we pursue this path, generally we face many hurdles and we approach a valley situation. And in fact, this valley could be much deeper than what we've seen here on this graph. And in some of these cases, the activation barrier becomes so high that all the pursuits of innovation die in this pit of the valley. And that's why we call it valley of death. So in order to translate from the initial discovery or invention or innovation and take it above this path of growth. So one has to cross this barrier. And so one has to build a bridge. And this bridge, unless it's built, then we get into this valley of death. Now, how one does and what would be the role of the scientists, engineers, entrepreneurs, or even venture capitalists or industry varies from place to place or occasion to occasion. And there is also no guarantee that this valley of death is only one single step. There could be multiple steps which actually poses impediment towards basic research or spin out and development, demonstration, and so on. So the cumulative effect remains that there is always a huge gap, and that needs to be bridged in order to take the inventions or innovations happening in the laboratories to the marketplace. And that is when know why translates to know how, and know how eventually translates to know what sells in the market. So I'll take a few examples. US, one of the leading nations in the world, at least in the modern times, created a major initiative called Definition of Grand Challenges. So there were 50 subject experts drawn from 40 different countries, with the Secretary of State, William Perry, as its chair. And they worked for more than 8 years and then came up and defined 14 grand challenges, which they thought would be the major issues to be confronted in the 21st century by the humanity. And they, of course, cover sustainability, health, security, and entertainment and everything. So they were very pointed questions like how to provide access to clean water, or how to make solar energy cheaper or economical or affordable. Very specific questions. India, in its own wisdom, also pursues similar problem definition course through what is known as Technology Vision. And here is one such example, which was chaired by none other than Dr. Anil Kakotkar. And this Technology Vision is 2035, but there was also another TV 2020, which was championed by late Dr. Abdul Kalam. So these are the exercises through which we try to define the major challenges that lies ahead of us. We made a different kind of an effort in 2015 through what is known as impacting research, innovation, and technology. The entire episode began with a fundamental question that India takes pride in showcasing the major IITs, or Indian Institutes of Technology, as one of the biggest brand names, which is internationally well known. Though they are institutes of technology, if one raises a fundamental question as to what kind of technologies have these institutes delivered, we do have examples, but not very many. Certainly, we are not comparable to the likes of Stanford and MIT. So in 2014, there was a brainstorming session, and eventually we decided that IITs now will lead such technology innovation mission. And it took us a year to define, and eventually on 5th of November 2015, the highest political leadership of the country blessed this initiative, none other than the Prime Minister and the President. And we launched this initiative with an aim for inclusive growth and self-reliance by translation of knowledge into viable technology. So what was different or unique about Imprint? Number one, it was for the first time an initiative which will address all challenges related to the engineering milieu. So that means any engineering challenge or issue faced by the nation will be addressed by this mission. Number two, it will be for the first time when all IITs, all major higher education institutions, including IISc, will take the lead and come together on the same platform. So they'll champion some of the causes, and they'll also invite industry and other institutions to join. And the most important thing was this was a mission when we would pursue not fundamental science alone, but we'll actually care for translation of fundamental science and knowledge into viable technology or product. So of course, fundamental pursuits remain important, but those of us who are also associated with translational research, this will be an opportunity and platform for us to showcase our readiness. So we divided the entire challenges into 10 themes. I think many of you actually in the audience were associated with it in various domains. So these were 10 domains defined. And these are, remember, domains defined from the user side, from the output side. So it is not mechanical engineering or electrical engineering. It is about energy. It is about sustainability, sustainable habitat. It is about water and river systems, and so on and so forth. So this is how we divided the entire spectrum of engineering challenges into 10 domains, and divided them into living world and material worlds domain. So at the launch of this mission, the Honorable Prime Minister mentioned that science is always universal, but the engineering solutions, when we devise them, should actually address to the local causes and needs. And this is how we said that the imprint initiatives should synergize with the major national missions that are already in progress. And we said that in any domain, if you have 10 specific themes, and if 10 themes have 10 particular issues and titles, so it already becomes 10 raised to 4. And then there are easily 100 variants because India is a major nation. So million challenges stands or appears formidable. But these million challenges are to be catered by billion minds. So we have enough resources, at least in terms of human resources, who actually can take care of such formidable challenges. So I'll just now move forward fast forward and say that after 4 years, we took a review. And in IIT Delhi on 4th of August, we arranged a technology exhibition to showcase some of the outputs of imprint. As I said, these are not necessarily meant for only publication or patents, not two-dimensional products, but three-dimensional products. And here are such examples of prototypes which were ready for commercialization, at least to go into field trial. So 1, 2, then 3, 4, 5. We actually showcased 75 such cases. And in fact, I'm sure Suman would be happy to see one of those examples coming from his own laboratory. I would like to now try and explain in next 5 or 10 minutes as to where lies the challenge and what is the difference between engineering and the so-called technology, between know how to know what sells. And I will borrow the examples or from my experience in CSIR system. I was fortunate to spend for about 3 years between 2010 and 12. And that is from Central Glass and Ceramic Research Institute in Calcutta. Dr. Jagtap would definitely identify these slabs of glass called the radiation shielding window glasses, which are used in the hot cell in Tarapur. So this is basically an enclosure in which you process the nuclear fuel, which are all radioactive elements. And even if it is spent or fresh nuclear fuels, they're highly radioactive, and you need a shielding window which not only will stop alpha and beta radiations, but even gamma, which is the highest penetrating one. So if you use borosilicate, which actually has the highest nuclear absorption cross-section, then you need actually a few meters thick glass. In order to reduce the thickness of the glass, you require higher density, and that is lead glass. So 70% of this glass is lead oxide, and which actually reduces the thickness by increasing the density. And this glass actually can be melted and processed only in one environment, and that is made out of pure platinum. So this technology took 4 decades for CGCRI to develop. And I use the word technology and not technique or not engineering, because only 3 nations in the world until then were able to develop these pieces of glass. And remember, in the limit, we require actually 1 meter wide, 1 meter in length. So such 1 meter square glass blocks, which are typically of the order of 80 to 90 or even 100 centimeter thick. So this glass pieces actually, as I said, are melted and cast in pure platinum glass. So this was a project which came from atomic energy. CGCRI worked for almost 4 decades. And I was fortunate that during my time, we completed the final delivery of this. It 20 ton of radiation shielding window glass. Now, why is it important? Because if the country needs to not only harness nuclear energy, but also use it for energy generation, then we need this capability. And if you are perpetually dependent upon one of those 3 or 4 nations, which only 3 nations, then anytime that access may be denied, and then your entire nuclear energy program can come to a standstill. So you require not only research initiatives, you actually require translation, which will undertake a very major initiative where out of 100 crore projects, 75 crore is meant only for one single component, which is pure platinum sheet, about only 1 or 2 millimeter thick, which can actually make the intervening layer over the refractory crucible so that the lead glass doesn't puncture and lead glass doesn't get contaminated. So this is where one has to realize that technology is a very different initiative altogether, different than just creating knowledge, different than just patenting a know-how. It is an initiative which actually requires very painful persuasion of a process which one has to perfect, because if you develop any defect in this window glass over a period of time or at the very beginning, then the refractive index changes, and that makes it impossible for the operator to see where the nuclear fuel is. So it has to be that perfect. CGCRI developed also several components and several prototypes for commercialization based on optical fiber. This is the only lab in the whole of Southeast Asia which actually has the capability of starting from a preform to draw the fiber and then eventually make devices out of those fiber, like this erbium doped fiber amplifier, which we use to actually accelerate and amplify the signal at regular intervals. CGCRI developed fiber Bragg grating, which actually can measure dilation as fine as a few micrometers. So if you have a certain structure, and if there's a dilation by only a few micrometers, and if you want to detect that dilation or change in dimension in a highly electromagnetic environment of 440 volts or even thousands of volts environment, where you don't have any human access, and at the same time you'd like to make sure that you are able to monitor the length change of these high tension transmission lines so that they don't snap without any prior indication, then you need a device based on this fiber Bragg grating. Those who are in the optical physics would certainly appreciate that this is not very easy, and moreover, to create such a device and then make sure that they're reproducible is also very, very difficult task. The hardest of them was creation of the supercontinuum source. The physicists know the worth of such a supercontinuum source, which is so-called the white laser, and actually can allow you to generate radiations anything from, let's say, about 400 to 1600 nanometer wavelength range. So over a very wide range, and this has multiple uses in very many applications. So this photonic crystal fiber based supercontinuum source also was something that was developed by CGCRI. And one other example is this hip joint prosthesis. So for patients who develop snags in their hip joints or knee joints, generally go for such replacements. A typical such component imported from abroad about 10 years ago would cost about 1.5 lakhs. CGCRI developed the same thing in 25,000 or 30,000 rupees. So about 1/5 or 1/6 cheaper than the imported component. More than 100 patients benefited from it. And these were operations were conducted mostly by one of the most famous orthopedic surgeon in the country, Dr. Sancheti. We tried our level best, and despite being so cheap and already proven and enjoying all the ethical clearances, still this product never could compete with the imported products. So that raises the important question that I'm trying to drive home. Then that it is not enough to prove the knowledge. It is not even enough to demonstrate a few pieces to earn the respect of the community. It is even more difficult, actually, or the most difficult task, or the last mile of the entire episode remains whether or not we are able to take it to the marketplace and make it available to the common masses. And so demonstration, there's something much more beyond. It's not economics alone. Probably we have to also worry about, in today's world, all those huge campaign blitz done by the companies, multinational companies, how to counter them. Now, these are all very high-end technologies. I'll give you one last example from CGCRI. For the big tiles or pieces of tiles we see as floor tiles or wall tiles and so on, the bigger ones until recently used to come all from foreign countries, including China. And to make those tiles, one needs something called Ukrainian clay. Strangely enough, this Ukrainian clay actually comes from Ukraine, used to come from Ukraine. And typically in these tiles made in the Gujarat, various factories in Gujarat, required about 20% by weight, so much of Ukrainian clay. So there was a lot of import bill and a lot of difficulties in having those materials. So our scientists in CGCRI showed that if you leach out the iron oxide from these local clay, then that clay actually through certain treatment could be made equivalent to Ukrainian clay. And when this was demonstrated, then 14 units overnight became 64 units, and each of them started making a profit margin or increasing their profit margin by more than 3.5 crore per annum per unit. And please remember, it didn't require a very major scientific pursuit or research. A simple application or innovation that if you can reduce the low melting forming eutectic compounds, then this same local clay can be actually used for making such big tiles. And we all know today that Gujarat, Morvi and Thangarh today are the biggest importers of such big tiles throughout the world. So this is where the innovation, even at the grassroots level, can actually be very, very handy. Now, through these four examples, what I wanted to convey is that in laboratories, we develop technique. In industry, we actually practice technology. So there's a subtle difference between technique and technology. And this is what is to be appreciated, particularly today, because today happens to be the technology day. So that's why I say that something which goes to that level can only, which can reach the market level, can only be called the technology, the ultimate technology. Now, obviously, the question arises as to what ails us, what is the difficulty for translational research. So it's a very painful process, time-consuming, and prone to risk or failure, very many risks of failure. Less rewarding. If you publish, you get immediately cited, or at least there is there's an acknowledgement or a record. If a technology attempt fails, you not only receive a very major setback, you also lose a lot of money. You need a large infrastructure, which is not necessarily available in small laboratories or not certainly in the academic institutions. There are a lot of rules and regulations which come in the way, which are not very conducive. We need a lot of initiative, and the output is not always quantifiable. You cannot say how much one has contributed to a technology development. And usually this is a teamwork, not an individual, there's no individual glory. It requires a lot of effort for translation, and it's very difficult to identify who is the real inventor or innovator. The commercialization mechanism itself, there's no easy formula for that. And to scale up from bench to the higher level is not so easy. And finally, we have a strange notion in the country that Lakshmi doesn't get along well with Saraswati. So as if someone who is pursuing knowledge is not fit for pursuing technology. And that is one of the biggest impediment. We all are aware that country is agog talking about the national education policy. I'm not going to discuss the importance of that. Would only like to mention that Indian National Academy of Engineering decided that we should take the lead in showing the path for translation and implementation of national education policy in the engineering and technology domain. So on our foundation day, the last foundation day, 20th April, we had a very important panel discussion preceded by 5 different satellite events. And these were addressed by industry leaders, by directors of national labs, directors of IITs, and also vice chancellors of non-government sector educational institutions. And at each satellite committee had at least one lady expert. So these satellite events, 5 of them, East, West, North, South, and Central, they gave their recommendations to the panel, and the panel deliberated upon that. And the panel was chaired by none other than Dr. K. Kasturangan, the principal author of National Education Policy. And it was participated by representation from Ministry of Education, University Grants Commission chairperson, AICT chairperson, industry leaders, directors of some of the institutions and vice chancellors of non-government sectors. So it was a very lively deliberations, and then we are soon going to submit our recommendations to the ministry. The final word about what we want to, we are all keen to make a difference to the country or its pursuit for progress. While we do that, we have to first understand that India is not a monolith. India actually is a psyche or a body of very many diversities. Diversity in terms of language, the region, the climate, weather, terrains, practices, food, culture, anything and everything. Yet we are a united nation. And that is why we have a history of 5,000 years, starting from the likes of Kanad and Aryabhatta. So we take pride in saying that we were the nation which first showed the decimal system, or was the initiator of the decimal system, or the inventor of zero. We have had the likes of Ramanujam and Satyen Bose, and also in recent times, a very celebrated scientists. But between the 10th century and maybe till the time the British arrived, our record of scientific pursuits and innovations probably is not all that glamorous. So now is the time when we should actually wake up, and already 70 years have passed from independence. The government of India has announced Azadi Ka Amrit Mahotsav, or Azadi at 75, the 75th anniversary of India's independence in this very year. So it is time that we prove that we actually can make a lot of difference through the synergy of science, engineering, and technology. So on one hand, we take pride in saying that we are one of the oldest civilization on earth, and also used to be richest, and not thousands of years ago, but even at the time of independence, or at the time till the Britishers arrived. We are one of the largest nation. We have a very large piece of land, a huge population, and a very large, this is old data. Right now we are looking at 3 trillion, and very soon we are likely to reach 5 trillion US dollar, and which is 6th in nominal and 3rd in PPP terms. So we are successful in science and technology in very many directions, in Mars and lunar missions, nuclear energy harnessing capability, satellite launching capability, and so on. And also life expectancy in the last 70 years has risen from about 25 to 65 or even more. So we have reasons to be proud about whatever little we have done in science and technology. But there's a flip side of the same coin, which says that, first of all, we have very many sources of diversity in the country, which are not conflicts, which are only realities in terms of diversity. We have an economy which is very large, but GDP per capita is not really glorious. We have a large population below poverty line. We have human development index wise, we are not really one of the highest, certainly lagging far behind. The gross enrollment ratio in various levels is not all that satisfactory. The innovation index wise, India is 46th in a list of about 100 odd nations. So we have a lot of challenges ahead in terms of poverty, hunger, healthcare, security, and very many things. And there are important solutions awaited coming from the engineering side in terms of energy security, country's defense, water, education, and so on. There are certain puzzles which says that 59% of our economy is contributed by the service sector. Agriculture contributes 14%, though agriculture is the sector where largest section of the population is involved. Industry contributes about 25-27%. In fact, manufacturing contributes not even 20%. So is only 11%. This is old data, but today it is probably around 20%. And Prime Minister aims that it should reach 30%. Now, country had 40% contribution from manufacturing at the time of independence. Today it is less than 20%, and is served more than 50% by the service sector. So this is not sustainable. If we want to aim $5 trillion economy in about next 10 or 15 years, then we have to certainly do something so that manufacturing is boosted and the economy is in stable ground. Similarly, if we look at the population growth, of course, we are growing and soon will be the most populous nation in the world. GDP is growing, we are happy about it, and we expect more. The energy demand, we still remain hopelessly dependent on coal. About 2/3 of our 390 gigawatt hour comes still from fossil sources. And that actually attracts a heavy penalty, a lot of criticism against India, that we are third largest contributor to the greenhouse gas effect in the whole world. Now, we also have to take the whole thing in the proper perspective. If India is the third largest offender in terms of CO2 emission, per capita emission of CO2 wise, India is way below the top 10 nations in the world. In other words, we are one of the largest, second largest population in the world. So there's a lot of aspiration in the population, which is also possibly the youngest population in the world. So unless there is a solution given, how can you deny somebody an access to the growth? So in that respect, we have to improve upon GDP per capita. There is improvement. In fact, this data has two colors. The brighter green is for 2000 data and more recent is lighter green. And as you see in every aspect of GDP per capita, energy demand per capita, oil demand per capita, coal demand, so all per capita basis, there is a significant improvement in all aspects. But what we actually need now is India-centric solution to the engineering challenges that we are facing today. And that is why translation of knowledge into viable technology and product is all the more important today than ever before. This is also another perspective that we all should appreciate well. So this is a backdrop where a canvas where we are trying to understand how is human technology development index, how that can be mapped to per capita primary power consumption, because we know very well that growth and prosperity is directly linked with the energy consumption or energy availability. So, and human development index can be actually quantified in terms of some of these very major parameters, and this is internationally accepted parameters. So HDI as a function of per capita primary power consumption follows a nearly accepted trend for the entire world. There are outliers. Germany is ahead human development index wise, so is US and Norway and some of the other countries. India is way behind. India is on the curve, but we have to cover up a large path ahead. And this is where, again, unless the country's economy is boosted without endangering the environment, and we ensure that there is enough energy security, we will continue to be busy in the job of catching up and not really being among the leaders. So let me move ahead. I mean, that's also very important that in terms of spending per researcher, per $1,000 spent, look at where is US, and we are actually even less than half. And there are countries, including China, Brazil, and so on, which are way ahead. So obviously the government outlay for research and translation of research, both must significantly increase. And another important part is that the R&D expenditure, percentage of GDP wise, is fairly low in India compared to some of the nations. Look at Australia, look at South Korea, look at Russia, where the R&D expenditure in terms of percentage of GDP is actually even higher or comparable to the weighted fractional count of the development. So obviously this gap needs to be bridged before we can aspire to be among the leaders in terms of technology and economic power in the entire world. So before I conclude, I'll just take 2 more minutes to say that what Indian National Academy of Engineering is doing in that respect. Obviously, we are happy and proud that we have about 1,000 fellows, out of which about 100 from foreign countries. And we are the sole representative of India in the International Council of Academies of Engineering and Technological Sciences. So what have we been doing to promote the culture of innovation and technology development? So INAE instituted with funding from DST something called Abdul Kalam Fellowship. And this is somewhat similar to the J.C. Bose Fellowship, with a difference that it is not celebration of somebody's already made achievements. It is essentially recognition of a talent and promise for technology development. So somebody writes a proposal, gets vetted, and then defends before a committee. Committee accepts, and we have allowed 37 such fellows to work on Abdul Kalam Fellowship. They get reviewed after 3 years. If the progress is satisfactory, then allowed one more term of 2 years, so 5 years altogether. So one single term for 5 years for technology development. It is only for translational research and not for fundamental research. It is only for demonstration of a prototype or to reach up to TRL level of 6 and above, so that the knowledge gets translated. We celebrate Engineers Conclave, where we choose 2 themes, one from the collaborating institute and one from the other part, who actually, who the host institution, who actually will take part in this conclave to pursue and come out with certain policy documents. We are a very strong proponent of civil infrastructure development. We have been trying very hard to impress upon the government that India should produce its own regional transport aircraft. We have had an expert group on clean coal technologies, and we have submitted our recommendations to the government. Similarly, we have also worked on automotive waste. We have INAE expert groups on such technology challenges, and we produced actionable recommendations for the government. We also are busy working on technological preparedness to deal with the national disruptions that may happen anytime. We have joint consultative committees with DST, DRDO, offices of the Principal Scientific Advisor, ISRO, CSIR, AICT, SERP, and DAE. And with all these organizations, we work together to propose certain policy documents, undertake certain joint initiatives, and offer the expertise of INAE on areas of mutual interest. We are very keen to pursue and develop a document which will be the roadmap for countries' energy security. And in fact, on 8th of December last year, we had a special event, and very soon INAE will create a special technology forum on developing a roadmap for energy security of the country. As a part of Azadi Ka Amrit Mahotsav, we are going to bring out 2 compendium, one on the landmark achievements of engineering and technology in independent India. We'll showcase 75 topmost achievements in the country. We'll also showcase women engineers, at least 75 of them, since independence. We run Youth Conclave every year with National Frontiers of Engineering. We also organize innovations in manufacturing practices. To promote entrepreneurship, we offer awards. We also undertake online exhibitions. We have a program on frugal innovations for nurturing frugal innovations at the grassroots level. INAE offers Young Innovator and Entrepreneurship Awards. We celebrate National Science Day and Engineers Day alongside also Technology Day. So we care for all science, engineering, and technology. Then we also have certain, we promote entrepreneurship, and we have also very many other initiatives of INAE, primarily to promote the concept of engineering, innovation, and technology development. So I'll end up saying certain things which are basically the conclusion of my thesis as to why or what really means the synergy among science, engineering, and technology. They basically are a triad where they're interconnected and they must feed into each other. So science is pursuing the truth relentlessly, regardless of its necessity or immediate scope of application. Science provides clues, if not answers. Science extends as far as imagination goes. Science never fails, but some scientists may. Engineering is all about enabling and providing solutions, borrowing from the fundamentals of science. Technology is the last mile for societal benefit based on scientific discovery and engineering innovations and inventions. So let us ensure as a nation that science, engineering, and technology in India complement each other and flourish together so that our society soon achieves the desired culture, growth, and prosperity. And in the words of the Prime Minister, Atmanirbharta. If India has one unique resource and strength that the entire world envies, that certainly is the demographic dividend. The youth, the more than 800 million people below the age of 35, and average age of the country very soon will reach 28. So engineering can ensure self-reliance and hence self-esteem. So with this hope, I certainly am sure that there is no individual in the country who would not believe that we don't need to treat science, engineering, and technology in isolated compartments, but rather believe that these three essentially are the apex points of the same triangle, which are all interconnected. The same person can be a scientist, engineer, or a technologist, and the same institution can do all the three activities in certain well-concerted manner. All it requires is a proper definition as to what is fundamental, what is translational, and how we facilitate that. And to that end, Indian National Academy of Engineering is always committed to pursue the path of science, engineering, and technology and its synergy. So thank you very much. I would like to end here, and thanks for your attention. Jai Hind.
Thank you, Professor Manna, for your very illuminating talk with this hypothesis and thesis. And I think the next speaker is basically going to prove your thesis and hypothesis, which is Professor Shuman Chakraborty, who is a professor in mechanical engineering and IIT Kharagpur, and he is also currently the dean research and development. And I was actually very, very impressed by his biodata because he's elected fellow of American Physical Society, but he comes from mechanical engineering department. He is a fellow of Royal Society of Chemistry, both are basic science, physics and chemistry. He is also fellow of American Society of Mechanical Engineers. So indeed there is a synergy between science, engineering and technology. He is fellow of all National Academies of Science and Engineering. Professor Chakraborty works in the area of microfluidics and microscale transport, and he has been a person who is a pioneer to amalgamate the science of microscale fluid mechanics, which is actually a domain of a physicist, and engineers with the complex biophysics of the cell. So that comes into really getting into technology. He is the inventor of paper and pencil microfluidic technology. It's not only an engineering but a technology. A new class of electrically manipulative miniaturized devices that does not require any sophisticated fabrication facility. His today's talk will be on Clipping with a Flow, Perspectives of Puzzling Fluid Dynamics and Human Health. Reconnect fluid dynamics with research.
Good evening, all the dignitaries who are present physically and also online. It is a great honor to be present on this platform, which I feel doesn't belong to an engineer like me, who always wanted to learn a bit of good physics, good chemistry, good mathematics, but ended up with something which I would say is a hybrid of maybe several things. I have deepest of my respects and regards for people who actually know physics, chemistry, and mathematics, and therefore this Institute of Basic Science is more than a temple for me. I'm very grateful to the present director and the former director, our own senior colleague, Professor Somit Ray, and the Indian National Academy of Engineering, led by the President, Professor Indranil Manna, and my other colleagues and fellows, for giving me this opportunity to talk about something which is actually an outcome of my own confusion. Is it science? Is it engineering? Is it technology? To begin with, when I was invited for this talk, I was a bit more tempted to talk about really the devices or the technology that we develop. But then I realized, no, I am going to an Institute of Basic Sciences. If I talk about that, then that will not be befitting the stature of the institute. So I came to a bit of adjustment, if not compromise, and this is what is an outcome of that. So all what I intend to talk about is, in a nutshell, fluid dynamics in micro capillaries and how it impacts human health. Fluid dynamics and human health is a very broad topic, and nowadays it's a one semester full course in many of the advanced programs. Therefore, I intend to be a bit more focused and talk about fluid dynamics in narrow capillaries, which are either inside human body or they are synthesized outside human body to understand some of the basic physiological mechanisms. And that is what is the motivation of the talk. Well, every subject, as it evolves, it has a history. Some of us who have studied a bit of science, bit of engineering, bit of technology, we have a feeling that history is not that important. And in fact, in our school days, we always used to think like that. But if we trace back the history of a subject like this, it is something which, out of a whole lot of effort, I could dig out from one of the old anatomical paintings with some Sanskrit annotation, which looks like an illustrated medical text on anatomy in the tradition of Ayurveda. I do not have the knowledge to dig into what is written here or what it talks about, but at least it reflects the tradition, the classical feel that perhaps as Indians we have always been having on this subject. But you know, having a feel on a subject and seeing it advance as a science is something different. In that respect, in many books, Leonardo Da Vinci, who was talked about, by Professor Mannais in one of his in his talks, that about the aircrafts that Da Vinci imagined at his era when it was simply a non-existent technology. Now, Leonardo da Vinci was like a genius. He was considered as a father of Renaissance, not just because he was a great in whatever he used to do, but he had a great fusion of vision, scientific knowledge, and artist sensibility in almost everything that he did, and anatomical drawings is one of those. He was the first to firmly state that the heart comprises 4 chambers in an era where, when it was believed, there was nothing to prove or disprove, but it was believed that it was made of 2. And the interdisciplinarity. His work in diverse fields led him to connect between soil and flesh, rivers and blood vessels. See, these are very disparate entities in the living and non-living world, and perhaps with a lot of imagination, and this kind of imagination is the hallmark of a great scientific personality. But Da Vinci's work could not be taken forward until and unless the subsequent researchers brought in what we call as groundbreaking findings in the domain. Why I'm telling all these things, because what I'm going to present today has a bit of prelude, bit of history. I should not present as if everything has fallen from just deep sky. William Harvey was the first physician to describe completely the systemic circulation and properties of blood as it is being pumped to the brain and the rest of the body by the heart. He first showed that valves in the veins, and you see the Gurukul, the valves in the veins were discovered by his own teacher, Fabricius. These valves permit the blood to flow in only one direction and not the other. Nowadays we all feel it is so obvious, but in those days it was not. And he was the first to postulate the existence of tiny capillaries between arteries and veins. The first, I would say, visionary of microcapillary or microchannel in human body. And these were more formally discovered. Maybe you can see that all the important milestones have 100 years of passage one after the other. In 1661 by Marcello Malfi. Now all these things have happened, and I do not really want to get into all these complex developments that led to the emergence of this fluid dynamics inside human body. But as a fast forward, anybody who has studied fluid dynamics in whatever subject, be physics in high school or elementary physics in college, or students from branches of like ours, mechanical or chemical engineering or civil engineering, who have very specialized courses on fluid mechanics or fluid dynamics, this is what we always look at. The famous Poisson Law. That is, you have a circular tube and fluid is flowing through that. What is the relationship between the pressure drop and the flow rate? Again, this law, how we study as a textbook material, was not in that form, and in fact, again, this is a person who was a great physicist, physician, all combined together, and his effort was fundamentally to understand how blood flows through microcapillaries. And to do that, he came up with a simple law which tells that if a fluid is flowing through a channel, and if it is not accelerating, that means it is called as a fully developed flow. There is no net unbalanced force. Then the driving pressure gradient and the resisting viscous force, they balance each other. That is what is that culminates in the form of the formula for pressure drop. And see the apparatus that in those days he built up to prove it. But all said and done, that law, although is very extensively used, doesn't always apply to our human body fluid mechanics, although the intention was there. And why? One of the major reasons, there are so many reasons, but one of the major reasons is that the walls of our blood vessels are flexible. They are not like a steel pipe, what is taught in engineering courses. The walls have different elasticities depending on whether they are of large artery, small artery, large small vein, etc. Even the most challenging is they are varying from one individual to another depending on the deposits and other things or the diseases that we all have. But these arteries, they distend when the blood pressure rises during systole and recoil when the blood pressure falls during diastole. So this was known for a long time. And Otto Frank, again you see, about 100 years subsequent to the previous development, he took the flexibility of these, at least the large blood vessels into account, and put up an analogy between electrical sciences and the fluid flow in the human body. So he put a capacitor model to consider the storage of this blood. Now all these advancements have taken place, and if we talk about these and we relate to what we learn as a textbook material, we feel very confused. Sometimes over the years when I have been teaching fluid mechanics to undergraduate and senior graduate students, I tend to be confused when I talk about first pipe flow. Flow through pipes is a bread and butter topic in any engineering, and flow through human body pipes, that is the blood vessels. So if you look at this hierarchical structure here, you have artery and vein, and that also you have large artery and arterioles like that. And arteries and veins are connected by a capillary network, which is the so-called micro-channeling human body. Now, why this is so important? I will give maybe one or two examples. And of course, it is very difficult to compare the complexity of these two. This is, one of the very advanced engineering plants. Look at it somewhere. You see the piping, and any engineer will say, "Oh my God, this is one of the most complex piping systems." Look into this. This is something where new blood vessels are growing during the progress of cancer. This is called as angiogenesis. When the cancer is progressing, dynamically new blood vessels they develop, and in that process, they result in proliferation of the cancerous traits to other locations in the human body, and eventually to metastasis during the end stage of cancer. So see, this is what is the dynamic progress of the human body pipes during the cancer progression. So absolutely, there is no sort of relationship or the complexity. Although this is engineering-wise very complex, no way near to the complexity of this. So engineering versus physiological flows, there are lots of differences. Not that today I will talk about all these, but I can talk about something, one of these, that is wide ranges of Reynolds number. Typically we can say that it could be a low speed to high speed flow from laminar to turbulent flow, unusual branching of the networks, what we see in the cardiovascular passages or respiratory passages. very unusual wall properties of the blood vessels. Why I say unusual? Because if you have steel as a material with a particular composition, everybody in the world will say that it has this modulus of elasticity. But you do not know what is the wall property of one individual under different conditions. Unusual pulsatility, the pressure versus time variation within the circulatory system. It is very unusual in a sense that it doesn't follow a sine or cosine periodic law, although many mathematicians tend to explain things in that. The rheology of the blood itself is very complex. It is by no means one of the very simple fluids. And the final point is the most important thing for medical science. It has a personalized variation. That means whatever physics, chemistry, what you put, at the end, there is a difference between what is going to happen in my body with your body. And that is very, very difficult to put up as a physics-based model. So blood is a complex fluid, all of us understand. And it is because that blood is, of course, what we see as a continuous matter, but blood has its own cellular components, the red blood cell, the white blood cells, and the platelets. But in terms of fluid dynamics, the major impact, direct impact, comes from the red blood cells, because not only they are of a large volume fraction of the total blood, which is called as hematocrit, about 40-45%, and 85% of the cells in human body are the red blood cells. And see that in human body there are many natural constrictions that occur, and when the constrictions occur, the red blood cells will deform absolutely in such a way. I have not put it up here, but from a biconcave disc, it can take up the shape of a bullet. It depends on the confinement. So it's not a standard Newton's law of viscosity that we are talking about. Not only that, these cells tend to get up or away from the wall of a blood vessel because of the deformation induced lift force that takes this cell away from the wall, and that results in the formation of a cell-free layer at the surface of the blood vessels, which is known as Hughes-Lindquist effect. Again, an effect which was brought out by these two medical doctors, but later on it was explained very carefully by engineers. Now, for a fluid dynamist, a simple way to imagine, like fluid dynamists, like basic physicists, will always try to understand the thing from a very simple point of view. So a drop of blood will be perceived as just a drop of liquid. But if you see what is all within that, the cellular matter, etc., we have to realize that it is not as simple as that, and the cellular matter which is there within itself has its own functionalities of a living system. A cell has life, and the life orchestrates many of the events in the human body, which is very difficult to explain mechanistically. Even then, there has been a lot of effort in explaining the mechanics of the red blood cells. So you have lots of effects due to bending, elasticity of the cell membrane, and viscosity of the cytoplasm. Together it is a viscoelastic material. All of us understand this, and I do not want to get into the details. Now, as I told you that the deformability, this is that picture that I was talking about, but I will not go through the details of this. That, let us say the red blood cell, typically 7-8 microns its the thickness. Now, if it is constrained to move through a channel which is itself 7-8 microns, it from a biconcave disc takes an absolutely elongated shape. And therefore, it is very important to understand that how the deformability, which is because of the passage of the blood through extreme confinements, is leading to the various cellular response of the blood, and that how it is connected to the health and disease of the human body. On the top of that, electric field, which is not normally applied in the human body, but it is induced because of certain electrostatic interactions, how that electric field influences the dynamics of the cells and their interaction with other cellular matter is another level of very complex activity. Why I'm talking about all these is not because I myself know all these answers, that how it exactly happens. But what I intend to tell, what Professor Manna was also talking about in a broad conceptual way, that here lies some unanswered questions in science. And if these questions are properly answered, then these can lead to technological revolutions. And how, I will show you some of the examples. Now, the physiology that I was talking about is physiology of the human body. Imagine that you have gone to a doctor and the doctor is trying to study what is happening in terms of, say, blood flow or cellular dynamics in your body. You don't expect that the doctor will do experiment on you. That means the doctor one day will say that you are a nice subject, so let me just do some probing inside your body and put some sensors and figure out what is happening. And all of us will say, no, I mean, your job is to just keep me well and make me well, but not do that kind of experiment where I can even die. So what you do, not just for understanding physiology, but also understanding the efficacy of the drugs that are being discovered and delivered. The traditional route is that in the lab, these are studied. Typical drug testing, the traditional drug testing. Then these are studied in animals. So typically you see the period of about 7 years, lab plus animals, and then another 7 years on human trials. So all in all, you have a 14-year long trial, and for due reasons. I mean, we have nothing to talk about that. And by that time, that impact of that discovery may not have been realized or may not have been utilized by the common people who are suffering from the disease. So how can we make it shorter? One way out is to make a human body-like connectivity on a chip. That means what happens in the micro capillaries in the human body, you make a small chip, artificially engineered biochip, where you replicate the microenvironment which is there in the human body. When I say replicate, it is a wrong word. You cannot replicate this complexity. What I mean as replicate is you replicate some of the essential, say, physico, chemical, mechanical, electrical features which are there in the human body as it is. Then you make some controlled study on that. You cannot make a controlled study inside human body. So that is what you do. And once you see that it has gone through certain positive outcome, then you pass it on to the animal trial and human trial. In that way, the lab portion of the trial you shorten. Not only that, the lab portion of the trial you make more effective, because the system is tried on a physical experiment which has nothing to do with what happens in the human body. It is completely disconnected, and then you try to apply on animals and humans is not a very fair way of doing the science. And of course, there is also a lot of ethical concern and gap between human and animal bodies. So anyway, if we can reduce that to an extent, that benefits. So in our research group, and not that we have been doing research on this particular topic for a very long time, but it is about 5 years. So I have some results to talk about. So one of my former PhD students, Dr. Kiran Raj, who has recently, he will join soon. He has recently got a faculty position at IIT Madras. So what I urged him to do is to develop a microchannel. So see, our vision is quite clear. Human body has microchannel. In microfluidics engineering, we make microchannels which are not similar to what is there in the human body. So the objective is to make microchannels which have much enhanced similitude of what is there in the human body. So there is a protocol which was followed, and the protocol is very, very simple. You can say the frugal way of doing it. So I'll just explain in a simple way without going through the slide. what you see here, if you have done any simple biology experiment, is a petri dish, and inside what you do is that you put a gel-like material. So before putting the gel-like material, this is a lumbar puncture needle. So typically you have this 250 to 500 micron diameter, and lumbar puncture needle is very commonly used in hospital. So not that you really have to get any special item out of this. So then this gel-like material, which is gelatin that we use, gelatin is a derivative of collagen, which is a protein very abundantly available in human tissues. So in loose terms, we can call it as a gel. So that gel is molded here, and after the molding, when you take out this lumbar puncture needle, you have a hollow microchannel. So in this hollow microchannel, what we try to do is to study first the collective dynamics of the red blood cells. That is, red blood cells as a collection, and this was the first study in the world which tried to show that what is the role, experimentally, what is the role of the deformation of the channel in the collective dynamics of the red blood cells. Prior to that, all the bioengineering studies were based on channels with very limited flexibility, no flexibility at all. So we put up controlled flow, and we used two different technologies. One is the particle image velocimetry, the PIV, to study the blood flow and blood flow as a whole, and particle tracking velocimetry to track the red blood cells, as Lagrangian particles at certain locations. And that is how we could look into the dynamics, the collective dynamics. Now, in the world of red blood cell movement, there are two very important types of motion. One, at low shear grade, it is called as a tumbling motion. So, basically an unsteady rotation type of thing. At high shear, when the deformation is very strong, from tumbling, it becomes a tank treading type of motion. And this transition is very important because the tumbling motion is supposed to endure a much higher drag in the human body circulation as compared to the tank treading motion. So we saw that with the deformability of the channel, this transition from tumbling to tank treading, this gets changed. So all what it means is that this tumbling to tank treading transition, which deals with a significant enhancement in the resistance against the flow in the human body pathway, that is strongly influenced by the deformability of the blood vessel. Now, once we studied that, the next question that automatically came, well, one microchannel is fine, but human body has a network of such microcapillaries. So one microchannel, there something will happen there, but how it will happen if you have a very complex microvascular network? So this is what is there in a human body, in a real human body, and what we try to do is now we try to extend this to in vitro engineering of this kind of platform. That is, on an artificial chip, represent a network-like structure, what microvascular network, what is there in the human body in an artificial engineered chip. So one of my PhD students, Josna, co-supervised by Professor Somen Das from the School of Medical Science and Technology, tried to look into this device fabrication. So what we did is, nature has inspiration to everything. So if you see a leaf has a very natural branch structure. So what was done here is that we try to use a technology which is called as nature-inspired soft lithography. So basically using a PDMS as a soft lithography molding instead of PDMS, it's a hydrogel molding here because of the gel type of material. I told that there are certain advantageous features, and then we developed these structures. But this was not replicating what is there in the human body. I mean, externally yes, but internally no. Why? You see the cross section of the the SEM image. It is not that circular lumen that is there inside the human body. So while we got the clue that it is very important to have a pattern or a mold which should look like this. It will require a different approach. So what we did is we tried to use the same design, this design, but we resorted to hydrogel molding technique. So what we did is we put a wire mesh of the network structure and then put up the dead gel material that I was talking about, and then flushing away the external part of the material. And when the wires were withdrawn after the solidification, you have the internal structure like this, and that is what is your network of microchannels, deformable microchannels with lumen, which is a circular lumen. But again, this is an engineered system. Is our blood vessel like that? So next what we did is we put an endothelial cell lining at the walls of these vessels. Our blood vessels at the wall have linings of endothelial cells. And this is very important because the linings of the endothelial cells have lots of functionalities. Not only that, they have certain protein layers called as glycocalyx layer, which have a lot to do with the biophysics of blood flow. So what we did is we put up that endothelial cell layer and then tried to study the dynamics of red blood cells and circulatory tumor cells. The circulatory tumor cells, as they are progressing, it's a simulated metastasis, you can say, outside the human body. So, and we could see that where the cell-cell tight junction is forming, the nucleus, we had different green and blue colored dyes to really stain all these. And whatever was summarily observed was very much consistent with what is there in medical and physiological literature about what happens in these systems. At the beginning, I talked about tumor angiogenesis. So, I'm just trying to add complexity one by one. So that was a static system of microcapillaries. Now, during angiogenesis, what happens? I will not go into the mathematical part, but I try to be more physical when I explain this. So when you have a stable blood vessel, so you can see these endothelial cells and our blood vessels have these linings. Now, the stage one, these endothelial cells, they will start proliferating. Why they will start proliferating? See, here is a tumor. Here is the first the cancer that is getting expressed, and when the cancer is getting expressed, there is a growth factor which is this VEGF. This growth factor, it has a very high concentration here and a low concentration. It's very much like diffusion. Because of the concentration gradient, there is a transport of the endothelial cell from the blood vessel to inside. And when it is transporting, it is sprouting new branches like that, and that way new blood vessels have been created. So this is the mechanism of how new blood vessels create during the angiogenesis. So we need a lot of mathematical modeling and computational fluid dynamics study to understand how it gets done, so that we can replicate that angiogenetic microenvironment on a chip. This replication is not yet fully complete or successful, so I do not have further results to present that. But I just want to tell that this is how research is happening. Now, why we do all this? See, fundamental science, engineering, but at the end, the technology. So the technology here I will talk about, and this is the my last point of this particular talk. That targeted drug delivery is one of the very important technologies in modern day clinical practice. So when you have a targeted drug delivery, one of the ways in which you can target the drug is by using different field effects. For example, magnetic field. So if you have magnetic nanoparticles, and the magnetic nanoparticles are used as a drug carrier, then these nanoparticles, under the action of a localized magnetic field, may target the drug to a diseased site in a very precise way, so that it doesn't impact adversely the surrounding healthy tissues. Now, in principle, it is fine, but whatever experiments have been done in the lab so far, these could not translate in the human body. The reason is very clear. All the experiments done in the lab on magnetically targeted drug delivery were based on rigid or non-deformable vessels, channels, and the real human body has a lot of deformability of the channels. So again, this is the first time that this was done by one of my postdoctoral fellows, Dr. Shomo Bhattacharya, who is currently now working in one of the diagnostic labs in Bangalore. So what he was trying to do is to put up a series of these magnetic nanoparticle messengers which will carry the drug. To begin with, we did not put up the drug, but we just tried to study the transport of the nanoparticles. So the challenge is that if I go back to the figure, maybe it is better to explain that you see that there is a fluid flow. So there are nanoparticles. Now you have a tendency that the particles either will be flushed away in the axial direction or be retarded because of viscous drag, but to the transverse direction it can only move under the application of the transverse magnetic field. This we understand in a magnetic drug delivery system. But what happens? Say the particle goes to the wall, but it has to penetrate the wall and get into the extracellular matrix where it will target the diseased tissue. So what is the role of the deformability of the wall of the blood vessel? That was the focus of this study. So what we did is, again, I'm not getting into the mathematical things, but in a very simple way, you have here a competition between the magnetic force which is trying to push it in the transverse direction and the viscous drag which is there in the axial direction. So if the magnetic force is very, very high as compared to the viscous drag, it will take it towards the wall at least. But too much magnetic force is, you have to put a heavy magnet, and that is not good for a human body application. So there has to be a good optimization of what is that optimal magnetic field which is needed. So what we did is, again, we did experiments based on some of the previous studies where magnetic nanoparticles were transported in a rigid channel. This is one of the previous work reported in the literature. So what we did is we tried to overcome that barrier and tried to develop a biomimetic lab on a chip for targeting magnetic nanoparticles. So this is the experimental setup that we developed, and you can see that there are different types. And these again, this is like a gel-like material which has functionalized layers and all those things, all the fabrication details that I talked about. And what we saw is that there is a very complex connectivity between the deformation of the channel and how the magnetic nanoparticles are captured. And in fact, over certain regimes, the deformation of the walls is helping the particles to penetrate. I mean, it is in a very, very simple way. You can see that had this wall not been deformed, this particle would have not, proliferated. But it is bulging in such a way that this particle has a, active path by which it could possibly penetrate. So these are all real experimental images, and what we try to do is to develop a conceptual understanding. And again, this is the partially complete study because we studied the transport of nanoparticles, but not so much specific to a particular type of drug. But it has helped to develop a lab on a chip technology. Now the question is that, well, lab on a chip technology which got its inception in early 2000, it has advanced to a great extent, and these are all advancing. And where we are all, converging to, there is a very, very fascinating area of research which is called as human body on a chip. So human body on a chip means your objective is to have different connectors and organ-like simulators, so that in totality the entire connectivity is something which gives us simulated environment of what could possibly be the transport in one of the, maybe connected to one of the organs in the body. But why the present day human body on a chip again is not successful in having a lot of impact on the medical or clinical influence? The reason is that those still consider non-biomimetic microchannels. That means microchannels which are very rigid, engineering-like rather than human body-like. Now, with the fabrication know-how that we have developed and we have demonstrated, if that could be adapted to the human body model on a chip, it could be one of the next generation technologies, biomimetic human body on a chip. This is something which has not been existing. About 10 years of research in human body on a chip have been over, but I think that this is one of the futuristic directions and in which research could go in this way, so that whatever is done by a bioengineer or maybe biophysicist is directly being used by a clinician to come up with a clinical decision making procedure, which we are quite close to that approaching, but still it is not there. Still, doctors have to use a lot of wisdom and knowledge on treating patients to treat them rather than using these fundamentals. So to summarize, dynamics of physiological flows, this has captured significant research attention, and complexity of blood flow in these physiological pathways is very unique. And fabrication of biomimetic microfluidic devices, which has been one of the very central themes of today's talk. This has given a very new perspective of this research, and this can be extended to study localized effects of magnetic field, electric field, or any other field effects. But at the end, because every individual is different, on the top of that, maybe individual variations can be accommodated by combined physics-based and data-driven approach. For example, if there is a medical imaging data on individual patient, that medical imaging data could be used as a template or a CAD model to produce a patient-specific human body on a chip model. And in that way, one can convert data science, that is AI, ML, etc., and physics-based knowledge to lead to a convergence where basic science really gets applied for clinical practice and the benefit of common people. Thank you very much for your kind attention, and I must acknowledge my various team members and professors, students, and other fellows who have contributed heavily towards doing this work. It is by no means a very complete work, but I thought that on a technology day, it is better to talk about something which is perhaps going to govern the cutting edge technology on one of the subjects, one of the very important needs of the entire world, which is affordable healthcare and health and well-being for all. Thank you very much.
Professor Chakraborty, for very interesting talk. I learned a lot of things. It's quite late, but if there are few questions, I mean, to all the speakers, all three speakers, if there is any, can take one or two questions. If there is any. Well,
Everybody is very tired.
it's a long day.
Yeah,
I know
long
that.
day.
Yeah, I have a question, especially on your last point, when you say it's a patient-specific or individual-specific chip that will be made. So, in what way it will be different from, the flexibility of the vessel? Is it different in different human beings?
Yes. So there are two things. One is the flexibility, and another is even the geometry or the architecture.
I see.
So let us say that some of us have these so-called plaques or deposits in the blood vessel. So if you have a CT scan or angiogram, you will see some signals in the medical image. Now that, to a large extent, could be emulated in these kinds of things. Regarding the properties, the mechanical property extraction of individual human system is again a very difficult job. Direct imaging cannot do that, but one can correlate, say, properties with the medical image through say data-driven model. Just a correlation. It's not really a basic science, but some data which is telling that if this is the image, then this could be the property, something like that. So that could advance patient-specific way of looking into this.
Is there any research or progress?
This is in a very elementary stage. Not much research has been done.
Okay, so I thank once again Professor Chakraborty
Thank you very
and
much.
all three speakers of today's event. I think in spite of the fact it was a long day, I think we all got enriched by three different speeches from three different perspectives. So thank you very much
Thank you
once
very
again.
much.
And may I now request Showman is there? Yeah, so just to say the forward thanks.
So, Honorable Chairman, governing body of SNBNCBS, Professor of IIT Bombay, Professor P.N. Jagatab, Honorable Director of SNBNCBS, Professor Tulsi Sadasgupta, and our former director and adjunct professor of Professor Shomit Kumar Rai, and our invited speaker, Professor Indranil Manna, Vice Chancellor of BIT Mesra, and Professor Suman Chakraborty, Dean RMD and Professor of IIT Kharagpur, attendees, ladies and gentlemen, on behalf of the center, it is my privilege to present a vote of thanks on the occasion of National Science Day 2022, organized jointly by the Indian National Academy of Engineering and SNBNCBS National Center for Basic Science. We are extremely grateful to our honorable guest, Professor B.N. Jagpal, for their gracious presence in the busy schedule and illuminating us about the National Technology Day. We extend my hearty vote of thanks to our most valuable invited speaker, Professor Shomit Kumar Ray, Professor Indranil Manna, and Professor Suman Chakraborty for illuminating talks on technology synergy and innovations. We are thankful to the Honorable Director, Professor Tulsi Sadasgupta, for extending her full support to organize this program in a very short notice. It's great pleasure to thank all the delegates and attendees for their gracious presence in this program, for making the program successful. We are thankful to all my colleagues and administrative staff of the center for their support to make the program successful. Thank you all again.
Excellent.
So, Tanushree, thank you, and thank you, Samit and Suman. I'll take leave now.
Thank you. Thank
Thank
you
you.
for being present, even from Delhi and all the, I know it was very difficult for you to adjust.
Oh, that's all right. I'm glad you organized this, and also thanks to Dr. Jagtap. Thank you, and bye-bye.
Thank you. Thank you.
আমি